Welcome back. In the last video, we worked through some notebooks using Keras with the sequential model, which is just the regular densely connected feed-forward neural network. In this notebook, we'll look at some variations on deep learning architecture, CNN, convolutional neural networks, RNN, recurrent networks, and variations of RNN, LSTM, and GRU. Before we get to those models, I want to talk about adding an embedding layer to a model. In this notebook, I'm using the movie dataset from the last video, and we're importing pre-processing in addition to the datasets, layers, and models that we've done before. We're using the same train test data, and what we're going to do is represent the first 20 words of each review in an embedding layer. I'll have a video on embeddings later, but the idea is you take the sparse matrices, like you see here, document term matrix, and you run them through a neural network to perform dimensionality reduction, visualized here. And that transforms the representation of each word. So in the document term matrix, each word is a sparse vector. As an embedded vector, it will have fewer dimensions, and all of the values will be floating point weights that were learned in this lower dimensional space. The pretty wild thing about embeddings is that it learns in a couple of different ways. One is that it learns by the proximity of words, and so it learns words that are related in some way. It can also learn using a target. In a later notebook, I'll show how you can use pre-trained embeddings, but here we're going to build our own. We want all of our input vectors to be of the same length, which is going to be 20 tokens. That's how we're going to use this pre-processing. These lines for both trained data and test data will chop it off at 20 words, and if it happens to be shorter than 20 words, it will pad it. In our model, after the embedding layer, we need a flatten layer to flatten the dimensions here into something that the dense layer can accept easily. I've only got one dense layer with ReLU activation, and the final dense output node is sigmoid. When we fit this, we end up with an accuracy close to 95%. We can learn word embeddings, as we did here, at the same time that we're training our model. So we're learning our own word representation. And again, I'll show you later how to use pre-trained embeddings. Let's talk about CNN, convolutional neural network. Using the same movie data, bringing it in, and pre-processing it the same as we did in the last video. This time we have our max length set to 500, so it will either chop it off or pad it to have a uniform length here. Our model is still sequential even though we have these convolutional layers. Here's our embedding layer. We're adding a convolutional layer with max pooling, another convolutional layer with global max pooling, and finally our output layer is one dense node. So let's talk about what convolving is. This spreadsheet is kind of my simple way of expressing the idea. The idea is that you have your data, which is going to be a bunch of real numbers, and what it will do is learn patterns in small windows. So that's this green box here. I'm showing a small 4x4 window passing over the data. And this is meant to show that it's already gone over the data here and moved once to the right. The stride or the step size here is 1. What convolving is a mathematical operation, and it could be as simple as dot matrix multiplication between this filter that we see over here, or sometimes called kernel, in the underlying data. Convolving just means you're taking two functions to create a new function. And it will also do dimensionality reduction at the same time. So this process gives convolutional nets two unique abilities. The first is that once a pattern is learned in one location, it will recognize it when translated to another location. CNNs are often used for image data because they can learn spatial hierarchies. For example, a first convolutional layer could learn local features like edges, and then later layers could learn how those edges and other features come to form really complex and abstract concepts like faces. So what we're learning with the convolving is a totally new representation. The Conv 1D nets have been shown to work pretty well with text data. In our convolutional layer, we've specified that we want 32 filters. Think of those like those green boxes we just looked at. And the filter or kernel size is going to be 7 by 7 with ReLU activation. By default, the strides parameter will be 1, and we'll use the default padding as well. Convolutional layers are often followed by pooling layers. Pooling layers will reduce the dimensions of the data and therefore reduce the number of parameters that have to be learned. This will shorten training time. Pooling can also help reduce overfitting. The variation of pooling here used is max pooling, in which the maximum value of a filter over window is used for the output. For example, a 3 by 3 filter will take the maximum of those 9 values as the one output for that window. And so you can see how that's a totally new representation of the data. The max pooling 1D layer will use a pool size of 5, and by default the stride size will be the size of the filter, which is 5 by 5. So we can see when we did our summary down here that the output shape will be the input shape minus pool size plus 1 divided by the strides, which in this case ends up being 494 minus 5 plus 1 divided by 5, which is 98. So we shrunk down here from 500 to 494 because of the filter going over the data. That process shrunk us a little bit. And then our pooling, we can see a pretty dramatic reduction in our dimensions here. Then we added another convolutional layer, followed this time by global max pooling, which is just like max pooling but doesn't reduce the dimensions. It may seem odd that CNN, which was really developed originally for image data, that it would work with text. So how does that work? I guess the short answer is that you can view text as a one-dimensional sequence of words, and so that's why a 1D CNN can convolve over spans of text to learn a more compact representation of the text. The rest of the notebook is pretty much what we've done before. We've compiled and trained and did a little bit of testing. Now let's look at the RNNs and their variations. Again on the same data, also using embedding, and then a simple RNN layer. RNN differs from a feed-forward sequential model because it contains a loop to iterate over sequences. Think of it like a for loop. And this for loop maintains an internal state that encodes information about what it's seen so far. So on the left in this diagram over here, we see that loop mechanisms. The X's represent the sequence of words coming in. And as it's processing, it's learning a hidden state represented by H. And if we unroll the loop so we get a little bit better intuition, we see that at each time step, a word comes in to the sequence and it learns a little bit more. And so it actually has a hidden state for every input and then a final hidden state. The compile, history, and training work just as usual. I trained for 10 epochs. Each one took about 13 seconds, and we got an accuracy of 83, which is not quite as good as the dense sequential model got. One problem that RNNs have is that they're trying to learn over long sequences of text, and that can lead to what's called the vanishing gradient problem, sometimes called the exploding gradient problem. So as you add layers, the gradient back propagation becomes smaller and smaller so that the training really is impossible. Problems such as this with RNNs led to the development of LSTM, which stands for long short-term memory. And this is an RNN that avoids that vanishing gradient problem. And the key is keeping the memory data path independent of the back propagation path and giving it its own update mechanism. So LSTM allows data to be carried forward, but also allows for forgetting some data, and that helps with that vanishing gradient problem as well. Here we're building the same model, this time with an LSTM. Notice training is longer, so it was 13 seconds for the simple RNN, about 23 seconds in epoch here for LSTM, but our accuracy was higher. Another variation of RNN is GRU, gated recurrent unit. It's a bit simpler than LSTM, so it uses less memory and it may train faster. In my case, it didn't actually train faster. And what it does is it combines the input and forgetting states of the LSTM. In general, it should train faster. Let's see what kind of accuracy we got here. It was between the RNN and the LSTM. This video provided a very lean and simple introduction to deep learning variations, CNN, RNN, LSTM, and GRU. The chapter discusses guidelines on which model might work best in different circumstances. This foundation should enable you to try these models in your own projects. Deep learning is about learning by experience, but keep in mind that the more you read, the deeper your intuition. There are links within the chapter to important papers on these different architectures.